All right, now we're going to take a look at how to find derivatives using some shortcut rules. So we took a quick look at several of them when I did that summary of the derivative rules. So now we're going to back up. We're going to look at just what's happening in 3.2. So in section 3.2, we're trying to find the derivative using some basic rules. Really those first four at the top of the other page. Let me see if I still have that open. So the first four on this is what we're going to be looking at to start with in section 3.2. And it's combinations of those four rules that allow you to find the derivative of a polynomial pretty quickly. Okay? So that's what's happening in 3.2. So we're learning how to do that more quickly. All right, so if you were using the limit definition to find a derivative, the limit definition wound up being looking at the limit as h goes to 0 of f of x plus h minus f of x over h, okay? And so if our function f were 3x squared minus 5x plus 1, what we wound up doing is we wound up finding and simplifying the difference quotient. So we went through all of this work. So that's the f of x plus h minus the f of x, all divided by h, and we wound up going through a lot of algebraic work. So we multiplied out the x plus h times itself. We distributed the -5 and the negative in front of all of this, which would change these signs. Then I'm going to distribute that 3 and bring along all the rest of this. And then a bunch of stuff cancels. The 3x squared and the negative 3x squared, the negative 5x and the 5x, and the 1 and the negative 1. And all you're left with are the terms that still have an h in them. The 6xh, the 3h squared, and the minus 5h. And so h really is a factor of the numerator. So you were able to knock out an h from each term, since it's just a single term in the denominator, and you're left with 6x plus 3h minus 5 at that point, and now you're ready to substitute the h in. This is the first time when you substitute the 0 in for h that you don't have 0 over 0. So you wind up getting just 6x minus 5. So the nice thing that we're going to be doing now in chapter 3 is we're going to be shortcutting this process. If we need the derivative of a polynomial like this, we're going to be using a combination of those first four rules on that other page to get right from there to there without all of that algebraic process. Okay, this is extremely necessary if we had a function that maybe had a polynomial like this that's degree 9. Can you imagine what would be required? We would have to wind up finding and simplifying the difference quotient would be practically impossible. Because taking that x plus h to the 9th power, while I could do it, it would take me forever. So instead, we notice some patterns and able to shortcut the process. And now, if we had started out with 3x squared minus 5x, what was it, plus 1, okay? Or if we had the function 5x to the 9th plus 8x squared, both of these are going to feel equally easy once you get used to using that combination of rules. So I'm going to go ahead and show you what we will be doing, and then we'll see the rules again on the next page and see how we're actually using several of them all at the same time. So when I get ready to do the derivative, one of the rules I'm going to use is the fact that if I have terms that are being added and subtracted, then it is okay to do the derivative of each term. When I take the derivative of that first term, I'm going to be using the simple power rule together with the constant multiple rule. The constant multiple rule says you can bring the constant down, and then you can do the simple power rule, which has me bring down the exponent, okay, and then subtract 1 from the exponent. So 6x is the derivative of the first term. Then I can go to the second term. And on that one, you get used to just knowing it's going to be minus 5. But on that one, it's really kind of like the first term. It's just there's an understood exponent of 1. So when you bring it down, oops, let me write it back one step. There's an understood exponent of 1. So when you bring the constant along and then bring down that exponent, the new exponent is 0, and x to the 0 is really a 1. So this is really 1, and you just get minus 5. Then we're going to use the fact that the derivative of a constant is just going to be 0, and so we wind up getting that final answer that we got earlier much more quickly. Okay? All right, now let me set my timer so I know when my video is getting long. All right, now it's just as easy to do this one. I can do the derivative of each term. I can bring the exponent down, take 1 away from the exponent, bring the constant out in front down, then bring the exponent down and take 1 away from the previous exponent, and then just simplify. Okay, and we're done that quickly. Okay, so it's just such a relief to be able to just do that instead of having to do the limit of the difference quotient. All right, but I want you to keep in mind one thing we learned. And the difference quotient is really the slope formula, right, in function notation. And we talked about how derivatives are really slope. And so keep that in mind as you're doing this, that what we're actually obtaining here at the end is a formula that gives us the slope, will enable us to figure out what the slope is at a single point anywhere on the original function. Okay? And that'll help you understand why you get like a 5 here. If you're thinking slope, you can kind of think about why that second term winds up having a negative 5, because it's just a linear term. All right, enough of that. Let's just go ahead and get busy with these rules. So here are the rules that we had on that other page. Okay, the simple power rule, the constant rule that says the derivative of a constant would be 0. Okay, so that's if f of x equaled some constant. That's a horizontal line, so the derivative equals 0 because the slope of a horizontal line is 0. Oops, I forgot I wrote those over to the right. So the derivative of 8 would equal 0 because this would just be a horizontal line up at 8. So it would have a slope of 0. Okay. Now the simple power rule has you, if you have a function that's something raised to a power, what it tells you is that when you're trying to do the derivative, you can bring the exponent down in front and then subtract 1 from your exponent, and so you're going to get a 5x to the 4th power. Okay? And it's the simple power rule because here we just have x to a power. We don't have like 2x plus 1 to a power. Okay. All right, now the derivative with respect to x of x turns out to be 1. so like f of x equals just x, then what we're saying is the derivative of that would equal 1, and here's why. Because it's understood to be to the first power. So you can bring the 1 down in front, okay, and then you'll have x to the 1 minus 1, and that would be 1 times x to the 0, and so that would be 1 times 1, which is 1. Okay, so now if the function had been, if f of x, let me write it over to the left over here. If the f of x had equaled 5x, then we could use a combination of that along with the constant multiple rule that we're going to look at in a moment. See, this right here, the derivative of it would wind up being 5 times the x has an understood exponent of 1, so we'd bring that down, and then we'd have the 1 minus 1, so we'll have 5 times 1. It'll turn out to be 5, okay? And that's what this is trying to say. The constant multiple rule says if you're trying to do the derivative and you have some constant times a function of x, like 4 times some function involving x, then you can just bring the constant, down. When you're doing the derivative, you can just bring the constant down and then do what you did with the simple power rule. Bring the exponent down, do 1 minus your exponent, go ahead and multiply those back and get a 12x to the second power. Okay. All right, and then here's that issue. If you have a constant times x anytime, so if f of x equals any constant times just x, the derivative of that, this rule right here is a special case of the constant multiple rule, is telling you that the derivative is 9. Easy way to understand that is because y equals 9x is a line with a slope of 9, and the derivative is supposed to be slope, and so that's why that turns out to be 9. Okay, so if it's just a constant times x to the first power, the derivative is whatever that constant is. Okay, and then with derivatives, if you have two functions that have been added or subtracted, it is okay just to do the derivative of each term and then add or subtract. So that allows us to do the derivative of a polynomial quickly and easily by using the combination of the rules we've talked about above. So here's the process. The constant can just be carried along, bring the exponent down, and subtract 1. Okay. Now, because it's okay to do the derivative of each term, that's what this is saying, then we just move on to derivative of 2x, which we know is just going to be 2, and then the derivative of negative 3, which we know is 0, and then just clean it up. So this would be 6x plus 2, and we're finished. Okay. Now, you may need to do some rewriting to take advantage of those rules. Okay. So you want to get, you want to take a moment to review the exponent rules we did earlier and understand a few other things that might help you. If you can create little mini power functions, then that means you can make use of the simple power rule. All right, so if you had something like square root of x to the third, you need to get used to doing things like that. That would be the same as x to the third raised to the 1/2 power, which is the same as x to the 3/2. And then when I go to do the derivative of that, I can think about it like a power function and bring the exponent down in front keep the x, and then subtract 1 from the exponent. So that would be 3/2 times x. And you need to get good at fractions. 3/2, 1.5. 3/2 take away 2/2, or 1.5 take away 1 would leave you with a 1/2 right there. And so your answer on this would turn out to be 3/2, and then got to get back into radicals, and that would be okay, or you could write it like that. So you sometimes have some rewriting to do. All right, now you'll sometimes have things like this, maybe something like that. Okay, now once you know the quotient rule, you could use the quotient rule on that. But if you understand some basic algebra, since x is really a factor of the numerator, there's an x in both terms up there and just a single x down there, can't I knock out one of those x's out of each term? And that's still, I haven't done a derivative yet, I've just simplified, and that way I can just use what we talked about. The derivative of 3x is 3, derivative of -5 would be 0, so the answer would be 3. So sometimes you need to do a little rewriting. Okay. All right, now later what's going to happen though is you might have a 3x squared minus 5x, but down here have an x, say -1. Well, then you're kind of stuck, because it's not okay. See, there's a minus here. The x is not a factor of the denominator, so I can't knock that x out of these two terms, and I'm kind of stuck until I know more. Stuck until you know the quotient rule later, okay? But even though I know the quotient rule, there are times like this case where perhaps I could get it simplified so that I could use some of those simpler rules. Okay? Same thing might happen with one like this. What if your function were something like x squared times 4x minus 5? Okay, so if I know the product rule, I could use it, okay, and you'll learn that. But even though I know the product rule, my preferred way of doing this would be to rewrite it as 4x to the third minus 5x squared by distributing, and then find the derivative by using those rules that we just talked about. Right? And getting 12x squared minus 10x as the derivative. And we'll pretty quickly, we'll get to where once we get it to here, we jump right to the derivative. We don't show quite so much of that in-between stuff, okay? All right, so you may need to use some algebra to rewrite your expressions. And that is where some of the problem comes in. You've got to worry about it. You've got to think about your algebra, your weaknesses, and try to fix some of the weaknesses you might have with your basic algebra, okay? All right, so let me stop the video there, and then we'll pick up with another video on this next part.